Good evening, and welcome back to the Sleep Journey. Today, we're drifting into a solar event, so brief, so intense, it still doesn't feel real. On October 29th, 2025, the Sun released 3 coronal mass ejections, one after another, in less than 9 minutes. Each eruption carrying billions of tons of charged plasma, each surge racing outward at more than 2 million kilometers per hour. And what made it unsettling was the geometry. They didn't fan out randomly. They seemed to line up, as if the Sun's own storm lanes were guiding them into one narrow corridor of space. And inside that corridor, something was already there. An interstellar visitor known as 3 Atlas, a body not born in our system, arriving from beyond the Sun's gravitational family. At that moment, it was at perihelion, its closest swing around the Sun. By every familiar expectation, this should have been the end, the radiation near the solar surface, the heat, the particle flux, the brutal physics of proximity. All of it says the same thing. An object like that should not remain intact, but it didn't. Vanish. Instead, as the 5 plasma front struck, its surface brightened, not the warm white of reflection, not the red of glowing rock, but a sharp, electric blue. Spectral lines tightened, like a signature coming into focus. And the brightness rose so fast, it looked like a mistake, more than 20 times stronger, in the space of moments. And still, as the Sun threw enough energy to shred stone, 3 Atlas held its line, steady, silent, unmoved, no obvious fragments, no recoil, no measurable shove-off course. Its path remained hyperbolic, open, unbound, a traveler that would never loop back again. For 38 minutes, it endured conditions that should have erased it, and when it emerged from the storm, it wasn't weaker, it was luminous, alive with an eerie glow, in wavelengths no ordinary comet is known to sustain, bluer even than the Sun's own light, and 3 different observing platforms caught the same impossible scene. SOHO, Stereo A, and GOES 19, different instruments, different vantage points, one shared conclusion, a small, unbound body, taking 3 direct plasma impacts and remaining essentially unchanged. Those minutes have already started to bend our assumptions about energy, about material strength, about what survival means in deep space, because what should have been a routine perihelion flare became a contradiction, a moment where familiar thermodynamics seemed to soften at the edges, as if the rulebook didn't tear, it simply stopped applying for a little. And inside that contradiction, a quieter question appeared. Did 3 Atlas merely endure the Sun, or, in some way, did it harvest the encounter? Welcome to our story, calm, focused, and told in the gentle language of the sky. If you'd like to join us again, night after night, you can subscribe and rest with these mysteries whenever you need. And if you feel like leaving a small mark, type Atlas in the comments, a single word, like a pebble dropped into a still pond. And if you'd like, tell us where you're listening from, and what time it is for you. A soft roll call from a world of quiet rooms, all watching the same stars. Stay with me until the end, because by the final chapter, you'll understand why a short, almost unnoticed moment may become one of the decade's most important observations. Now, let's begin. At 1342 Universal Time, on October 29th, 2025, 3 Atlas reached perihelion, the closest point of its path to the Sun. For weeks, observatories had prepared, expecting something familiar, a brief outburst, a predictable brightening as frozen gases heated and boiled away, the classic comet story. But when the data arrived, it wasn't gradual, it was immediate. Across active instruments, from coronagraph cameras to solar monitors, the same change appeared at the same time. The brightness curve didn't climb like a hill, it rose like a wall. Perihelion is often the most chaotic moment for a comet, the moment of maximum stress. Normally, an icy body rushing inward warms at the surface. Trapped volatiles escape, creating a coma, a soft cloud of gas and dust. Energy in, vapor out, brightness up. It's a pattern we understand. But 3 Atlas refused the familiar rhythm. Its luminosity surged, passed 100-fold, within minutes. Too fast, too clean, too steady. And there was something else. No obvious breakup, no explosive dust jets, no spreading debris field, no visible tearing. The glow looked uniform, stable, and intensely blue. In basic comet physics, brightness follows distance. As a body approaches the sun, its activity increases along predictable curves. For typical comets, those curves steepen modestly, 3, maybe 4, as the distance halves. But 3 Atlas implied a slope near -7.5, a technical detail, with a simple meaning. Each time its distance to the sun was cut in half, its brightness multiplied not by tens, but by something like 200. That is not ordinary sublimation, that is something else. And, 2. Scientists, a reading like that points to 2 possibilities. Either the instruments were lying, or a different energy process was happening. So, they checked the calibrations, again and again, and the simplest doubt collapsed. 3 separate spacecraft, built by different teams, in different orbits, cannot all misread the same way, at the same moment, in the same direction. Then the conversation moved to color, because the light was not the familiar gold of reflected sunlight. It was blue, measurable, repeatable, consistent. To glow that blue by pure heat, a surface would need temperatures beyond what we expect from a small dark body, and before the encounter, 3 Atlas appeared cold, dim, unremarkable. Reflection alone doesn't make that color. The evidence leaned toward emission, light produced by the material itself, not merely borrowed from the sun. As it passed behind the solar disk, moving near 89 kilometers per second, it endured radiation, intense enough to soften iron. Yet the orbit stayed smooth, no visible change in spin, no obvious loss of mass, no measurable deviation. It passed through the storm and kept going. Astronomers began calling it a perfect contradiction, a fragment from another star's, a neighborhood surviving one of nature's harshest environments. If it were a standard comet, it should have unraveled long before perihelion. If it were a typical rocky asteroid, thermal stress should have fractured it, but it did neither. The closest pass lasted less than an hour, yet its echo will last decades, a reminder that interstellar visitors may not behave like the bodies we've studied for centuries. They arrive carrying chemistry, structure, and history, forged in places we can only imagine. What 3 Atlas showed that day wasn't only heat resistance, it was mystery. A body that brightened beyond prediction, glowed bluer than expected, and remained strangely stable. It went into the light and came out, unchanged. And in that moment, the universe seemed to whisper, we still don't know what matter can do when it comes from beyond the stars. Long before it brushed sunlight, before any headline, before any formal report, 3 Atlas was already different. The first hint was hidden in its path. Its motion didn't fold into an ellipse, the way planets and long-period comets do. It opened outward, hyperbolic, one word, with a profound consequence. This object was not bound here. It was passing through. If you picture a planet's orbit, you imagine a closed oval, a loop that returns again and again. But a hyperbola is an open road, a trajectory with too much energy for the sun to hold. Once it passes, it will not come back. 3 Atlas was one of those wanderers, a fragment that may have drifted for millions of years between stars until gravity finally guided it into our neighborhood. When astronomers mapped its speed, they paused. Near perihelion, it reached around 89 kilometers per second, too fast for any ordinary slingshot inside our system. Even Jupiter, the great thrower of comets, couldn't easily account for that entry energy. The simplest answer was also the strangest: interstellar origin, which means it carried material from another sun's domain, chemistry, structure, and a history written under different light. Its incoming angle was steep, cutting through the planetary plane like a blade, more than 40 degrees off the ecliptic, not part of the orderly traffic of solar debris, a stranger moving through a crowd. At first, it was faint, a small shimmer among countless points. Ground telescopes saw it as one dot among many. But its motion gave it away. Night after night, it shifted faster than nearby asteroids. Automated systems flagged it, Orbit fits tightened, and within days, the decisive number appeared, eccentricity greater than 1, a simple value, and an absolute declaration. This object was free, and once that was confirmed, observatories around the world turned toward it. Because every hyperbolic visitor is a sample from another star's workshop, it may carry isotopes, minerals, and volatile mixes formed in alien environments. For planetary scientists, it's like catching a messenger from beyond the local bubble. For physicists, it's a gentle test. Do the laws we use hold everywhere, or do they bend subtly, depending on cosmic history? And 3 Atlas seemed to blur categories. Like the earlier interstellar visitors, it carried echoes of both rock and comet, reflecting light like a solid body, yet developing activity like an icy traveler. That dual nature softened the borders. Was it a frozen shard or a carbon-rich core, a relic from another system's outer reservoir, or something broken from a larger parent? Some even whispered about artificial possibilities. Not as a claim, but as an uneasy question. And the hyperbolic path made certainty difficult. We can't easily touch what won't return. As it approached the inner system, simulations traced its incoming direction toward Lyra. The uncertainty stretched across light years. But the idea remained. It may have been expelled from a young system, long before Earth existed. It could have wandered silently for eons, its surface scarred by cosmic radiation, its interior preserving an old abyss, chemistry. By the time it neared the sun, it had traveled farther than any human-made object has ever journeyed. It wasn't coming for us, not by intention. It was drawn by geometry and chance. And yet, in that geometry, there is wonder. One curve on a chart proves something beautiful. Our solar system is not sealed. Space is not empty. It is filled with travelers, each carrying a story from a different beginning. 3 Atlas was one of them, a hyperbolic stranger passing through our light for a brief, then slipping back into the dark. When astronomers describe comet behavior near the sun, they often speak in curves, brightness rising in a steady relationship as sunlight warms the nucleus and gas escapes. For decades, those curves have obeyed familiar physics. Closer means brighter, but within limits the mind can hold. Then 3 Atlas arrived, and the limits seemed to fail. In the hours around perihelion, the data showed a flat climb that fit no standard model, not a gentle incline, but a sudden surge, a spike sharp as a cliff face. Technically, its brightening implied a power law slope near 7.5. To most people, that number is just a number. To an astronomer, it's a warning. Typical comets sit between -3 and -5. Even dramatic outbursts rarely push higher than 6. 3 Atlas went beyond. Mission teams reacted with disbelief. Maybe calibration, drift, maybe solar glare contaminating the signal, but independent instruments confirmed it, one after another. Stereo A, SOHO, goes 19. Each recorded the same steep acceleration, within margins too tight to call coincidence. Whatever was happening was real and fast. 2. Understand why it matters. Picture what a power law describes. It links 2 changing things. Here, brightness versus distance from the sun. A slope of -4 means when distance halves, brightness rises about 16 times. A slope near -7.5 means the same change multiplies brightness by well over 180. That isn't a normal escalation. It's runaway behavior. For it to occur naturally, something would need to release energy more and more rapidly as heating increased, as if each degree triggered an internal cascade beneath the surface. Yet, there was no visible breakup, no sudden tail blowout, no expanding debris cloud. The light intensified, but the body stayed coherent. Violence in luminosity paired with mechanical stability. That combination presses hard against the expectations of thermal physics. Some scientists proposed buried supervolatiles, carbon monoxide, carbon dioxide, sealed under dusty layers, materials that can erupt at lower temperatures than water ice. But even those explanations struggled. Volatile bursts usually flare, then settle. Pressure equalizes, activity levels out. Here, the brightening persisted and kept climbing for hours. Others wondered about microscopic chain reactions, dust grains charging under intense radiation, releasing energy in coordinated discharges, sending waves through the coma, a mechanism that could brighten without shattering. But that too had trouble matching the data, because the ascent looked smooth, continuous, almost disciplined, exactly what coronagraphs showed. When the light curves from all platforms were layered, the line rose nearly straight up, no gentle rounding, no oscillation, just a relentless climb into a plateau of blinding intensity. Analysts used a familiar phrase, a saturation event, not because the senses were saturated, but because the signal itself pushed beyond expected bounds. For a moment, it was as if the universe turned a dial, past what our equations allow. A few observers offered a different framing. What if the object wasn't simply reflecting? What if it was emitting? If sunlight was being absorbed and then transformed and re-radiated into visible light through an unknown process, the curve could rise this sharply. It would suggest 3E Atlas wasn't only heated, it was converting energy, almost like a natural amplifier, quietly turning solar violence into coherent glow. As it rounded the far side of the sun, the brightness finally leveled, but it didn't return to earlier levels. It stayed luminous, stable, and distinctly blue. The steep curve wasn't a momentary glitch. It marked a transformation, and for astronomers, that single measurement became a challenge, a test of the foundation of comet science itself. If one interstellar body could break the usual rule of 4 and sustain a slope like -7.5, then assumptions about energy transfer, sublimation, and surface composition may need revision. The question shifted, not why did it brighten, but how could reality to permit it? These numbers will be studied for retested, debated, remodeled, recalibrated, and even if later analysis softens the slope, the memory will remain. A visitor from another star, reaching into the solar system's predictable rhythm and drawing a 20-line, almost straight upward. A moment that made scientists wonder whether light can be more than reflection, more than heat, perhaps even a message written in physics we haven't learned to read. Yet, then came the color data. At first, analysts assumed an error because the numbers implied something almost poetic. Light output bluer than the sun itself. Comets are usually white or slightly reddish. Dust tends to scatter and absorb in familiar ways. But 3 Atlas leaned hard into blue. And in astronomy, color is not just appearance, it's process. The sun's visible peak sits near yellow-green, where its temperature radiates efficiently. A comet that reflects sunlight usually inherits the sun's color, may be tinted by dust, but to register bluer than the solar spectrum means producing more short wavelength light than reflection can account for, higher energy photons. In plain terms, it looked like the object was generating light, not merely borrowing it. And the effect appeared across independent platforms. Stereo, A. Soho, goes 1.9. Different sensors, different filters. The same shift toward the blue end, not a marginal change, not within casual error. Statistically, strong. Several sigma beyond normal. Once cross-referenced, ambiguity faded. Whatever 3 Atlas was doing near perihelion involved emission behaving as if the object were hotter than it should. Bluer than the sun sounds like poetry, but physically it means extreme excitation. Shorter wavelengths carry higher energy. For a small body to produce that, it must either reach extraordinary temperatures or use a mechanism that channels energy directly into high-frequency emission. Both options strain comet physics. The first natural explanation reached for known molecular bands: cyanogen, diatomic carbon, gases that can glow greenish-blue under ultraviolet stimulation. Comets sometimes show a faint green hue for exactly this reason, but those effects are usually confined close to the nucleus, a small inner coma. 3 Atlas displayed blue emission across a region about 300,000 kilometers wide, roughly 25 Earth diameters. That scale is hard to sustain through ordinary fluorescence. The energy requirements become enormous. Another idea pointed to scattering, the way Earth's sky turns blue. If the coma contained ultrafine grains, smaller than visible wavelengths, they could preferentially scatter blue light, but comet dust is typically larger, and submicron grains near the sun should not survive long. Even if they did, they likely couldn't create the intensity measured. So some considered a more radical mechanism: plasma emission. High-energy electrons in the solar wind striking molecules, kicking them into excited states that radiate visible light. This happens faintly around planets and occasionally around comets, like a gentle aurora. If 3 atlas carried conductive material or an unusual magnetic interaction, it might behave like a plasma antenna, converting charged particle energy into visible emission. That could explain both the blue color and the sustained brightness without the usual dust production, but it would also demand conditions, density, field strength, organization, beyond what's been clearly observed in typical comet plasma. Then came the most uncomfortable interpretation: material properties, photoluminescence, substances that absorb ultraviolet and re-emit visible light. Certain carbon structures can do this. Polycyclic networks, complex organic frameworks, and yes, engineered coatings can also do it. No one rushed to claim intent, but the comparison lingered because the glow looked less like burning and more like activation. To eliminate instrument issues, engineers dissected every stage of the pipeline. They checked for vignetting, stray light contamination, detector bias, and processing artifacts. None could reproduce the consistent cross-platform blue shift. Each instrument's calibration history ran deep, refined, through countless solar observations. For all 3 to misread the same way would require an almost impossible alignment of errors. So by early November, teams largely agreed on one point: the color was real. The debate changed tone. Not, did it happen, but what mechanism could do this. If the blue light came from natural chemistry, then we were watching physics pressed to its limits. If it came from plasma organization or structural fluorescence, then 3 Atlas was interacting with the sun in ways no ordinary comet has shown either. The implication was profound. In a universe where color often tracks temperature, this small traveler seemed to outshine its host star in energy per photon for a few short hours. It turned the familiar, warm solar glow into a backdrop for something colder in feeling, yet sharper in light. A reminder: sometimes the strangest color in the sky isn't illusion, it's a new kind of glow we've never had to explain before. The blue shift that shouldn't exist. When the first processed GOES 19 frames appeared, image analysts suspected a lens artifact, a bright ring, too wide, too symmetrical, too luminous to belong to a small interstellar body. But the measurements held. Around the nucleus, a vast self-luminous envelope appeared, stretching roughly 300,000 kilometers across, about 25 Earth diameters, more like a gas giant's magnetosphere than a transient comet coma. Comets usually carry a faint halo, produced by vaporized surface ice. That gas reflects sunlight and fades with distance. Color is neutral, sometimes slightly green, but this envelope broke the pattern. It wasn't only brighter than expected, it seemed to radiate its own light, and in wavelengths that didn't match simple solar reflection. 3 independent instruments confirmed it. Stereo A saw it in its coronal imaging, Soho's LASCO recorded the same extension, and GOES 19 captured the most complete time sequence. Hundreds of frames, a luminous sphere, holding steady, expanding only slightly as the object rounded the sun, and the brightness remained remarkably consistent even as viewing geometry changed. It wasn't a fleeting glint, not a momentary flare. It persisted, a glowing cocoon, moving with a traveler from beyond the stars to sense its scale. Imagine Earth at the center. The glow would swallow our planet and still extend far, beyond, hundreds of thousands of kilometers, into space. Inside that enormous volume, particle density must have been thin, and yet those sparse particles produced enough radiative power to compete with reflected sunlight near the sun. That balance challenges familiar thermodynamics. In a normal coma, luminosity fades as gas disperses. Here, the outer edge stayed nearly as bright as the inner region. Photometry teams considered resonance fluorescence, molecules absorbing ultraviolet light and re-emitting visible bands, carbon monoxide, carbon dioxide, can glow in blue-green under certain conditions, but even at peak efficiency, known molecular bands struggle to sustain a smooth, massive, luminous sphere like this. The emission appeared too uniform, too continuous. It lacked the flicker and line-dominated texture typical of molecular fluorescence. Another possibility returned to plasma. The near-Sun environment is thick with charged particles. If 3 Atlas had conductive surfaces or unusual magnetic behavior, it could interact with the solar wind in a way that produces large-scale luminescence, electric discharges, electron, excitation, a glow not from heat, but from energetic particles. In laboratory language, it would resemble a vast plasma chamber, a halo where electrons move along invisible fields. Yet no known comet has shown this at such scale, and the symmetry remained puzzling. Blue bias toward shorter wavelengths, the same deep tone found in spectral analysis. Blue light can imply high-energy emission or very fine scattering particles. If it were dust, it would require an almost perfectly distributed field of ultrafine grains forming a hollow sphere. Nature rarely builds such clean symmetry, and still, hour after hour, the envelope did not collapse. It lingered like a translucent shell. 3 Atlas continued along its hyperbolic path as the shell stayed wrapped. Around it, when the sequence was plotted in motion, the envelope looked almost stationary, while the nucleus traveled through its center, as if the light itself had inertia. That led some observers to wonder, was it more than illumination, a boundary layer, a place where magnetic pressure and radiation pressure found a temporary equilibrium? In mission logs, envelope of light began to replace coma because it didn't behave, like a cloud, not a tail, not jets, not a typical emission field. It seemed like its own structure, a glowing sphere that resisted the decay expected of transient gas. As 3 Atlas slipped behind the sun, the envelope expanded slightly more and still held its brightness. It faded mainly when the viewing angle placed it directly against the bright solar corona, where its light blended into the background. Days later, when the object reappeared, the sphere was gone, leaving only a narrow residual glow. What formed that envelope remains an open question. A natural plasma shell, a resonance unique to interstellar chemistry, or the optical footprint of material we have not yet catalogued. Whatever the cause, the event was real. For a few hours around perihelion, 3 Atlas carried a sphere of light larger than most worlds, a luminous boundary surrounding a traveler from another star, and it left us with a gentle reminder: even the emptiness of space can shine. And for all the attention it demanded, the most extraordinary moment still happened where no human eye could watch directly. Behind glare, behind distance, behind the sun's own brilliance, a quiet transformation, recorded by instruments, and then carried into our dreams as a story, a brief visitor, a sudden blue glow, a cocoon of light, and the calm realization that the universe still has ways of surprising us. And tonight, as you rest, you don't have to solve it. You can simply let it be, a soft mystery, moving through sunlight and slipping back into the dark. And tonight, as you settle deeper, you don't need to fix the puzzle. You can let it rest, unfinished and gentle, a quiet mystery, drifting through sunlight, then slipping back into the velvet dark. On October 29th, 2025, as the visitor brushed perihelion, it passed straight behind the sun from Earth's point of view. For ground telescopes, it simply disappeared, lost in the white glare where daytime washes everything away. No sparkle, no tremble, no hint, just absence. And yet, while our eyes on Earth were overwhelmed, our eyes in orbit were not. Solar conjunction is one of astronomy's quiet blindfolds. When an object wanders too close to the sun in the fani, its faint light is drowned, and observers must wait for days, sometimes weeks. A pause built into the universe's viewing angle, a silence enforced by brightness. But spacecraft don't share Earth's exact geometry. From their drifting vantage points, they can hide the sun's center and study the faint halo beyond. They can shade their instruments and peer into the corona's delicate glow and that's where the secret of 3 Atlas was preserved. While Earth-based astronomers could only predict where it should be, Stereo A, SOHO, and GOES 19 were already recording what it was doing. Each satellite carries a coronagraph, a camera with a small artificial eclipse. An occulting disk blocks the sun's blinding face, so the dim regions around it can appear. These tools were built for solar storms, for flares, for coronal mass ejections. But now and then, they catch something else. A comet skimming by, a small traveler passing close. Usually those encounters are simple. A speck brightens, stretches, then fades, a brief flare of ordinary physics. But 3 Atlas did not follow the usual rhythm. During the hours it was hidden from Earth, it produced what scientists later called a luminous episode. The coronagraphs watched as its brightness surged far past what normal sublimation could explain. The images arrived in clusters, frame after frame, each one stranger than the last. At first, controllers suspected the sun itself, a wandering arc of plasma, a solar feature drifting across the view. But when they traced the bright point's motion, its track matched the predicted path perfectly. The anomaly wasn't on the sun, it was in front of it, racing through space, only a few million kilometers above the star's surface. Imagine the view, a dark circle where the sun has been masked, surrounded by a pale ghost of corona. And inside that mist, a single point swells. Then, it seems to bloom. The light shifts from ordinary pale brightness into a hard, electric blue. It spreads evenly in all directions. For nearly 40 minutes, it outshines the surrounding structures. Then, instead of collapsing, it steadies, it holds, quiet, balanced, as if it has found a new equilibrium. And on Earth, no one knew. Even the signals carrying the evidence had to cross the same noisy region. Solar interference delayed the radio stream. By the time ground stations received the packets, the moment had already passed. Hours later, teams processed the frames at places like the European Space Operations Center and NOAA facilities, and realized they had witnessed something extraordinary without seeing it happen live. There's a calm irony there. For centuries, we've treated the sun as revelation, the light that exposes all. Yet at the precise instant the universe staged its strangest scene, that same brilliance blinded us. The sun became both theater and curtain. Only later did astronomers rebuild the geometry. Along its hyperbolic passage, the alignment tightened, Earth, Sun, and the object sliding into near-perfect overlap. Just minutes before the brightening peaked, the visitor was hidden at the exact moment it defied expectation, as if the cosmos performed the experiment behind a veil, letting only our instruments bear witness. That concealment deepened the mystery. If the flare had appeared in a night sky, millions might have watched. It could have become folklore overnight. Instead, it unfolded in private, captured by sensors built for solar weather, not interstellar visitors. Only after the data were decoded did the full shape of it emerge. The luminous envelope, the blue bias spectrum, the unshaken stability. Behind the sun, 3 Atlas carried out its quiet defiance. No backyard telescope saw it, no human eye caught it, and yet the proof remains, stored in the digital memory of our spacecraft, a record of something unusual, just beyond the reach of ordinary vision. For a few brief hours, a traveler from another star entered the one part of the sky we cannot comfortably stare into, and there, unobserved by people, it broke the star familiar rules. Every astronomical mystery begins with angles, the relationship between observer, object, and light. With the wrong alignment, even a brilliant event can vanish in plain sight. 3i Atlas became a perfect example. What made the discovery feel solid wasn't one camera or one data stream. It was agreement, 3 separate spacecraft, far apart in space, all registering the same impossible behavior in the same window of time. Distance turned a strange signal into a verified event. At perihelion, Stereo A, SOHO, and goes 19. Occupied 3 different posts in the Sun-Earth neighborhood. Stereo A traveled ahead of Earth in its orbit, far from us. Watching from a shifted viewpoint, Soho hovered in the gravitational balance near the cos. Sun-facing line, keeping steady watch of the solar disk, goes 19, built mainly for weather, remained close to Earth in geostationary orbit, yet its instruments could still glimpse the region, near the Sun's masked edge. Together, they formed a triangle of observation, not planned, not choreographed, just geometry, being quietly helpful. Each spacecraft carried different hardware, different optics, different filters, different strengths. Stereo's wide images were made for tracking motion across large fields. Soho's LASCO system carried decades of calibration and trust. GOES 19 offered a faster rhythm, capturing frames more frequently. So when a signal appears in all 3, the anomaly probability of shared error drops fast, and when 3 Atlas flared, the 3 lines of sight were separated by tens of millions of kilometers. If it had been a mere reflection, a sensor ghost, or a transient solar filament, each platform should have seen it differently. Different timing, different shape, different placement, but the pattern held. In all 3 sets, the event began within the same narrow window, rose toward a similar peak ratio, and occupied the same relative coordinates beside the Sun. Perspective ruled out coincidence. Triangulation also offered distance, a slight parallax, a subtle shift between viewpoints that lets analysts locate an object in 3 dimensions. That analysis confirmed something crucial. The luminous source was not a coronal feature, not a solar flare masquerading as motion. It was an independent body, exactly where orbital models placed 3 Atlas. The match was precise, down to fractions of a Fordant degree, not a glitch, a real object, moving and unbound. This geometric cross-check became the spine of the official reports. Without it, skeptics could have blamed solar noise. With it, they had to accept an interstellar visitor truly brightened beyond expected limits. Those differing viewpoints even helped estimate the envelope's size. Comparing apparent diameters from each angle, researchers derived a physical scale near 300,000 kilometers, a number later supported by photometric measurements. Beyond the math, the geometry carried a quiet lesson. Perspective matters, literally, and in how we reason. One observer can be fooled by glare, by assumption, by bias, but 3 observers, separated by space and method, can reveal what a single view might miss. That is the soft power of triangulation, in astronomy and in science itself. Soon, the data were layered into composite visualizations. The merged reconstructions showed 3 Atlas gliding through the corona, its halo expanding, its core staying steady. Each viewpoint contributed a slight depth cue, turning flat images into a 3-dimensional story. For the first time, humanity watched an interstellar object interact with our star from multiple angles, a scene captured in stereo, in every sense. Among mission scientists, the arrangement earned a nickname, the Triangle of Proof. Accidental, yet perfectly timed. No one scheduled that geometry, but it arrived exactly when it mattered. And in the end, confirmation didn't come from belief. It came from separation, from distance, from the way perspective turns doubt into clarity. 3 quiet spacecraft, spread across millions of kilometers, looked toward the same furnace and saw the same impossible glow. Their lines of sight converged on one conclusion. 3 Atlas had done something extraordinary, and geometry, once again, delivered reality from illusion. In astronomy, brightness is a kind of language. Every flare, every slow rise, every fading tail is a sentence written in light, and if we read it carefully, we learn the physics beneath the glow. For most comets, brightness is a simple conversation. Sunlight warms ice, ice becomes gas and dust, and those particles reflect light back. The pattern is familiar, approach, and the glow increases, recede, and it softens. But 3 Atlas didn't speak that gentle dialect. It spoke sharply, as Stereo A, Soho, and GOES 19 tracked the perihelion passage. Their light curves revealed something unsettling. The rise was not smooth, it was sudden, not a curve, but a wall. To scientists, the difference is everything. A slope suggests gradual heating, predictable sublimation, ordinary dust reflection. A wall suggests runaway behavior, a process converting energy into light, faster than equilibrium. Should allow. At first, teams moved carefully. Near the sun, instruments can exaggerate changes, a source crossing a field of view, a slight shift in pointing, a detector's thermal state. Analysts checked orientation, background, models, sensor health, but no instrumental story matched the place, numbers. When flux was plotted against time, the curve looked almost exponential. Brightness climbed more than 100-fold in less than an hour, then steadied as if the object had entered a new, stable mode. Brightness is more than reflection, it is energy flow. Light can come from scattering or from emission, from atoms and molecules releasing photons after excitation by heat or electricity. The spectrum suggested emission dominated. The light carried extra weight in shorter wavelengths, blue, violet. Not what you'd expect from simple reflected sunlight. Something was transforming energy on site. So researchers converted the observed brightness into estimates of radiant power, even conservative. Calculations implied staggering output, tens of billions of watts, briefly, enough to power a small nation. And yet the object itself was no larger than a mountain. No known comet or asteroid has emitted that much visible light without tearing apart. Normally such luminosity would mean jets, fragmentation, violent mass loss, but the orbit didn't show recoil, no measurable acceleration, no wild tail dispersion. It brightened without obvious shedding, and that contradiction opened a new question. Could the brightness be revealing material properties, not just outgassing? If the surface contained compounds that glow under ultraviolet, it might convert solar energy into visible light, efficiently, like phosphors or certain luminescent materials. A process like that could create intense brightness without huge mass loss. It fits part of the pattern, but it stretches what we've observed in nature. These kinds of energy conversions are well known to laboratories, yet they're rarely seen on cosmic bodies at this scale. Brightness also reveals structure. In typical comets, the inner coma is brightest, then fades outward. GOES 19 showed something eerily uniform, a wide glow, almost like a shell. That evenness suggests the emission was not localized. The whole envelope appeared active at once. Either sunlight was being trapped and scattered inside a dense cloud, or the region was energized throughout by a plasma process, lighting every point at the same time. Either possibility is astonishing, and the timeline of the glow is what makes it harder to ignore. Most bright bursts in space cool down, thin, out, and quietly disappear, but 3 Atlas didn't fall back into darkness. Even after it had moved outward, away from the fiercest heat, it kept a surprising share of its shine. That lingering light suggests something important. This wasn't just a single, it behaved more like a steady mode, a higher setting that the object reached and then held. For researchers, brightness is a kind of cipher, and sometimes it's a gentle alarm. When an object remains luminous, past the point where cooling should win, it usually means our picture of its interior is missing pieces. Either the object carries substances that can bank energy and release it with unusual efficiency, or it is operating in conditions we haven't learned to model correctly yet, and the simplest summary became strangely bold. 3 Atlas acted like an emitter, not a reflector. Its glow read less like borrowed sunlight and more like its own output, near perihelion, for a short, unreal span. This interstellar visitor seemed to speak in radiance, as if brightness in the universe is not only about being seen, but about endurance, about steady power, about something that does not hush even under the sun's pressure. When the first packets finally arrived through the solar data pipeline, the mood wasn't celebration, it was stunned silence, because the figures refused to line up. Curves that normally describe comets, from old sublimation laws to newer interaction models, couldn't carry the weight of what the sensors reported. The rise was too abrupt, the hue too shifted toward blue, the motion too clean, And all of it happened after the object endured repeated solar violence and kept moving, as if nothing could push it off course. It had been a long time since the mathematics failed so completely. Usually, science grows by small disagreements, a tiny offset, a faint wobble, a manageable puzzle. But this wasn't a puzzle piece, out of place. It felt like the whole frame had cracked. Every familiar expectation pointed to the same ending. A close pass near the sun should mean loss, erosion, jets, fragmentation, and then a fading trail. But none of that arrived. The first idea to collapse was the simplest one, classic sublimation, the notion that ice near intense sunlight must rapidly boil away, even tough. Heat-resistant material has limits, yet the infrared readings did not show a runaway temperature. Instead, the surface seemed to level off, well below the numbers predicted by standard heating, almost as if incoming energy was being handled, redirected, or shed in a way we don't normally see. Some scientists used a careful phrase, thermal protection, not as an answer, but as a placeholder, because no agreed mechanism could explain it. Then attention turned to another breakdown, the idea that ultraviolet light should tear molecules apart, snapping bonds, turning solids into gas. The brightness implied heavy energy exchange, so the chemistry should have been loud, but the expected chemical shouts never appeared. No strong surge of typical radicals. No clear spike in water-related lines, no familiar distress markers. In simple terms, it shone like something burning, yet behaved like something intact. That contradiction pushed many teams toward a different toolkit, not chemistry first, but charged particles and fields. One proposal centered on particle excitation, fast electrons, and solar wind ions, striking material and producing aurora-like light. This path can generate glow without requiring heavy mass loss. But it asks for something rare, a meaningful magnetic structure in a small wandering body, a trait we don't usually associate with comets or asteroids. GOES 19 tried to detect signs of that environment, and the results didn't offer an easy confirmation. The field readings looked quiet. If a magnetic system existed, it was either faint or masked, or arranged in a way the instruments couldn't isolate. Another idea then rose, equally strange, but chemically grounded. A surface layer that converts harsh ultraviolet into visible light. A kind of deep, dark material that turns invisible energy into blue radiance. On Earth, we can manufacture coatings and structures like that, materials used in energy devices and light-emitting applications. If 3 Atlas carried anything similar, it could appear brighter the more it was bombarded. But nature rarely produces such behavior at scale, and stability under extreme heating is even rarer. Many such structures require precision, the sort that doesn't easily predict today. Survive cosmic time, which is why probability became part of the conversation. Spontaneous formation in interstellar space seemed unlikely, and each explanation demanded a different kind of miracle. Plasma interpretations needed, coherent electromagnetic behavior, photoluminescent ideas, needed unusual compounds and unusual stability. Thermal protection challenged energy accounting. Every route forward created a new contradiction. Scientists found themselves circling. Answer one question, and another breaks. Models that had been sturdy for generations suddenly felt delicate. The discussion widened across the world. Some urged caution. Maybe this was simply an extreme but natural alignment, composition, angle, and timing. A rare combination that looked impossible, only because we had never witnessed it in this exact way before. Others offered a different warning. If something truly new was in the data, then forcing it into old assumptions would delay the very understanding we were seeking. By mid-November, a phrase began showing up in notes and exchanges, quietly, repeatedly, theories under strain. It didn't mean magic. It meant the universe had moved ahead of our equations. What happened wasn't against nature. It was against our current descriptions of nature. And that might be the gentlest truth in science. Every law is temporary, not because it's wrong, but because it's incomplete, waiting for the next edge case, waiting for the next test. 3 Atlas became one of those tests, a pressure point on our assumptions, a clean crack in the old picture. It reminded physicists of something humbling. We can calculate heat and motion, and trajectories, yet still not fully understand what light can do, especially when matter is unfamiliar. In the end, the object offered no tidy explanation, only a stack of mismatched clues. But clues like that are not failure, they are fuel. They turn certainty into curiosity. They remind us the cosmos isn't required to behave in ways that feel comfortable. So teams moved to the next layer. They looked closer at the spectrum, hoping chemistry would provide a simpler story. In astronomy, light is a fingerprint, gases and dust absorb and emit at specific wavelengths, and those thin lines and bands tell you what an object carries. But here, instead of clarity, the spectrum added more tension because the pattern looked familiar and unfamiliar at the same time. The process began with careful removal, subtracting the solar background, filtering out the haze of plasma, isolating the object's own signature. When that cleaning was done, three features stood out most clearly: a carbon-related band, a cyanogen band, and a faint third structure that didn't neatly match the usual comet catalogues. Carbon signatures and cyanogen are not rare in comets. They often contribute to the subtle colors in a coma, but the balance here was strange. The cyanogen contribution appeared too strong, and the carbon feature looked shifted, as if the molecules were in an unusually excited state, not merely warmed, but driven, in terms. The surrounding molecules behaved less like a sunlit cloud, and more like material inside a controlled plasma environment. Excitation levels suggested frequent collisions and energetic electron transitions, the kind you expect in dense, confined conditions. The solar corona can energize matter, but usually in ways that are broad and fleeting, not neatly sustained around a small traveler. To rule out instrument quirks, independent teams compared platforms, ESA groups, NASA groups, ultraviolet. Channels on SOHO showed related anomalies, and optical channels on GOES hinted at the same shape. Even lower resolution sensors still echoed the pattern, so the lines were real. What was off was the state of the stoned molecules, not the detection. One explanation was fluorescence, molecules absorbing ultraviolet, then re-emitting invisible light. Fluorescence can look bright without requiring extreme heat, and it could account for the odd strength and shifts, but scaling that process up to the size of the observed envelope requires constant pumping, a steady delivery of energy, like ongoing bombardment by charged particles, which loops us back to the same unsettling implication. 3 Atlas might have been interacting with the solar wind in a way we hadn't seen before. Another possibility was internal supply, as if gases were being fed outward continuously from within a sealed structure, not in bursts, but as a smooth release. Yet the data didn't show repeating spikes, no rhythmic eruptions, no obvious venting pattern. Instead, the glow stayed even, balanced, distributed, like a system that had found a stable operating point. Then the third, spectral feature, demanded attention, faint near the border of ultraviolet and visible, in a region often linked with metallic ions, nickel, magnesium, but the proportions didn't look normal. Nickel appeared unusually dominant, and stranger still, the signature looked like nickel without its usual companion, iron. That pairing is uncommon in natural bodies, because in most formation stories, those elements travel together, born from the same stellar processes. So a nickel-heavy signal without a matching iron pattern felt like a mismatch in origin, a hint that this material wasn't assembled in the usual way we expect comets to be assembled. That finding reopened broader speculation, carefully, without headlines. Maybe this wasn't a typical comet nucleus. Maybe it was a fragment of something more exotic, a rare planetary remnant, a stripped core, or a piece of material formed in a highly unusual chemical environment. No one needed to claim anything dramatic. The data itself was already dramatic. And still, the team stayed disciplined, because molecular analysis is supposed to settle arguments, temperature, pressure, composition. But here it only deepened the fog, the cyanogen to carbon balance, the stubborn blue emission, the metal lines that didn't pair correctly. Each result seemed to contradict the last. When you stacked the clues together, a new picture began to form. Not of a passive object, but of matter that responds actively to energy, as though it channels incoming power instead of simply suffering it. Months later, researchers tried to imitate the signatures in controlled settings, hoping to recreate those lines. Some tested carbon lattice structures, others tried ionized carbides and unusual alloys. Again and again, the match stayed out of reach, close but not exact. The spectrum remained, its own strange accent, and slowly a conclusion settled in. Maybe chemistry alone wasn't enough. Maybe the meaning wasn't only molecular, but architectural, built into structure. Whatever 3 Atlas was made of, it didn't seem to come from the same familiar workshop that produced most of our local comets. Its light carried the feel of a different history, shaped by another star, or by conditions we haven't learned to reproduce. And when the blue glow refused to be explained comfortably, the field of discussion shifted again, back toward plasma, back toward charged matter. It wasn't an easy turn. Plasma is famously unruly, not quite gas, not quite solid, moving to rules that depend on electromagnetism, not only gravity. Yet the growing evidence made the plasma framework harder to avoid. The earliest clue was simple: the way the light refused to fade. The sustained halo didn't behave like heat glow, and it didn't behave like a brief chemical flare either. It held steady, even as distance increased. That kind of persistence suggests ongoing power, a living interaction, not a dying ember. So the central idea sharpened. What if 3 Atlas was acting like a conductor, not merely catching sunlight, but coupling with the solar wind? Near the sun, space is thick with fast particles, protons, electrons streaming outward. And when that stream meets conductive or structured material, currents can form, and light can appear in sheets and arcs, like aurora, written on a much larger canvas. If the object carried even a modest field, or a geometry that can trap and guide charge, it could gather particles, accelerate them, and build a radiant cocoon, not a flame, but a plasma-born glow. And in that possibility, the Dorblizer story takes on a new kind of quiet, because it suggests the brightness was not a wound, but an interaction, not destruction, but coupling, a visitor, meeting a star, and briefly turning the storm into light. And when those gentle flickers were measured, the pattern didn't look like noise. It repeated, with a steadiness that made engineers pause, a rhythm too, even, to be blamed on chance. Researchers compared the timing to known wave motions in plasma, the kind of magnetic ripples that travel when charged particles sway along invisible paths, and the match was uncomfortably close. It suggested the halo was more than glow. It behaved like an active electromagnetic weather system, breathing, responding, in step with the solar wind. For that kind of environment to form, 2 things would have to be true. The object would need to carry conductivity, and it would need to hold a stable magnetic shape. Conductivity is easier to imagine if the surface included metallic grains or carbon-rich material that can carry current quietly. But the second requirement, the organized structure, was harder to place inside a comet-like body, because a small cold traveler shouldn't have an engine for magnetism, no molten heart, no lasting dynamo. Yet the signal implied order, not chaos, not scatter. Either the object arrived already magnetized, a relic of its original home, or it preserved alignment in its skin, as if its surface held a faint, enduring memory through the long dark between stars. To make sense of that idea, teams reached for familiar cousins, places in our own system where bodies couple electrically with their surroundings. A moon that feeds currents into a giant planet's magnetic field, a planet whose upper atmosphere glows when the solar wind presses in. In each case, charged particles meet structure, and light appears along lines you can't see. 3 Atlas seem to take that principle and stretch, though it not just a small patch of aurora, not a faint ultraviolet trace, but a full visible envelope spanning an enormous region with power levels that felt wildly out of scale. Then came the hard part. Simulation after simulation asked the same question. How? How much energy can the solar wind deliver to something this small? Even with generous assumptions, the numbers came up short. To reach the observed radiance, the conversion would need to be startlingly efficient. A fraction so high it made some researchers shift in their seats, because nature is often messy, and such clean efficiency is rare. Skeptics offered a softer possibility. Maybe geometry did the trick. Shape, spin, orientation. If the body were elongated, rotating, it could generate changing electric potentials as it cut through the charge flow, like a moving conductor passing through a field, charging, discharging, charging again. The exact rotation rate was hard to pin down. Perihelion glare hid the usual surface markers, but the periodic tremor in brightness left the door open. A hint, not a proof. As the weeks unfolded, additional solar monitoring records helped translate the blue tone, the color aligned with signatures, consistent with highly excited ions, carbon, oxygen, common elements, but not commonly seen in that level of energized state. That fit a plasma story, because plasma doesn't just warm matter, it strips it and then lets it recombine, releasing light in precise bands. By the time the analyses matured, the plasma framework rose to the top, not as certainty, but as the least impossible map. It described 3 Atlas as a solid traveler wearing a skin of trapped charge, a luminous sheath held in place by field geometry, neither a simple comet nor a quiet rock, but something between, a body surrounded by a temporary atmosphere made of electricity. And still, one question refused to settle. How does an interstellar fragment arrive with conditions so perfect for this kind of behavior? Was it a rare coincidence? Composition meeting timing, shape meeting storm, the right corridor of solar wind at the right moment? Or was there a deeper order hidden inside what looks like randomness? For now, no one can say. But the plasma idea gives the mystery a name you can hold, a way to describe the glow without breaking physics. And then, as the final orbital solutions arrived, a quieter kind of wonder emerged. Because despite the violence, despite heat and radiation, despite the luminous shell, its trajectory stayed clean. No measurable drift, no detectable shove. The path, calculated weeks before, remained almost perfectly unchanged. That is strange for any object that vents, because venting creates recoil, the same simple principle as a rocket: release material one way, move the other. And comets do this all the time, tiny, non-gravitational, nudges that add up, that bend predictions just enough to measure. So when scientists saw a massive envelope and an apparent outpouring of energy, they expected the orbit to show a small disagreement. But the data stayed stubbornly aligned. At first, some suspected smoothing. Perhaps the glare near the sun had hidden subtle shifts. Yet, with 3 separated vantage points and careful cross-checking, the conclusion held within the limits of observation. The motion looked gravitationally pure, as if the brightness had no mechanical cost. That contradiction landed heavily because energy exchange usually leaves fingerprints in momentum. If the object was truly radiating at huge levels and interacting strongly with the charge stream, then somewhere an exchange should show up, a push, a drag, a tiny acceleration, but it didn't. So physicists explored balancing acts, maybe opposing forces cancelled, or perhaps the radiation was so symmetrical it thrusted equally in all directions, leaving no net change. In theory, a near-perfect symmetry could create brightness without motion, but nature rarely builds perfect symmetry. Comets crack, vent through, weak spots, produce jets, not balanced spheres. So the steadiness suggested either a breathtaking coincidence or a kind of order we don't usually assign to small bodies. The plasma model offered one escape. If the light came from trapped particles, circling within fields, rather than mass being expelled, then thrust might be minimal. The glow would be a surrounding phenomenon, not a jet, more resonance than recoil, a sheath that shines without the nucleus throwing to itself forward. Still, even there, radiation, pressure from sunlight should contribute something. Yet the perturbation looked smaller than expected, and that led to even stranger language. Ideas about surfaces that handle photons in unusual ways, redistributing energy so momentum cancels. On Earth, engineered structures can do hints of this, but finding anything similar as a natural relic between stars felt improbable. Other minds reached for density. Maybe the body carried so much mass that tiny forces couldn't budge it, measurably, but dense exotic matter doesn't neatly rhyme with a luminous blue halo, so the shorthand grew: pressure without push, a poetic phrase, for a physical discomfort. It described a traveler moving through solar violence as if it were passing through rain, not stopped, not steered, just unchanged. And in the records, the arc remained, a line drawn before perihelion, still tracing the sky after it, as if the sun had pressed, and the object had simply refused. And that refusal became part of the legacy, because in science, meaning often rises from comparison. We understand a thing by setting it beside another. So, as researchers tried to place 3 Atlas inside a broader story, they reached for the only true peers we have, the earlier interstellar visitors, the quiet one in 2017 and the comet-like one in 2019. Together, those few objects form our entire, confirmed sample, and yet 3 Atlas did not fit comfortably between them. The first traveler showed little to no visible activity, a dim body, oddly shaped, tumbling, and then a subtle, non-gravitational drift, motion without obvious light. The second looked more familiar, a comet with dust and gas, brightening and fading in patterns we recognize, alien origin, but familiar behavior. And then came 3 Atlas, where the symmetry flipped, radiance without drift, light without recoil. One challenged mechanics, another reassured chemistry, and this one challenged the way we connect both. Side by side, they framed a boundary of ignorance, like 2 distant poles, and a third point that refused to sit on the same map. That contrast stirred late-night debates. How could consecutive visitors from the same vast galaxy show such opposite, impossible traits? Was there a whole continuum we simply haven't seen, because our surveys missed them, because they moved too fast, too faint, too briefly? Or were we looking at different categories entirely, different histories, different architectures, formed in environments that do not produce familiar outcomes? The absence of intermediate examples became a silence of its own, a missing chapter, and it made every interpretation feel fragile. When the record is this small, every anomaly feels like a message, and every message can be misread. So, even as public imagination reached for big ideas, researchers stayed careful, but the thought still lingered between the lines, not stated loudly, but never fully gone. What if interstellar space carries more than debris? What if some fragments are not accidental, not a claim, just a question that appears when comparisons stop making sense? And 3 Atlas, glowing, stable, unmoved, kept that question softly alive, and that's what made the comparison so unsettling. Not because either object was mysterious on its own, but because together they formed a pattern that didn't feel random. Both of them passed close to the sun, and both refused to fall apart the way we expect. Both left behind behaviors that could be read 2 ways, as chemistry, pushed to extremes, or as something electrical, something field-driven, quietly shaping what we saw. And between them, there was a long hush, years of sky surveys, years of watching, with no clear middle case, no gentle bridge, from one story to the many other, only a gap that sat like a question mark inside interstellar research. How could 2 visitors from the deep dark arrive so close together in our timeline, and yet behave like mirror opposites? One, with motion that didn't, to match its visible output. The other, with visible output that didn't match its motion. It forced a broader possibility into the room. Maybe there is a whole spectrum of interstellar bodies, and we've only caught the extreme ends. Maybe we missed the quieter ones, the dim ones, the fast ones, the ones that slip past our instruments before we can name them. Or maybe the galaxy throws different kinds of matter into motion, not one family, but several, each shaped by different birthplaces, different pressures, different chemistry, different histories. For Oumuamua, the cautious explanations gradually gathered, not perfect, but at least grounded. Ideas like hydrogen, leaking in a way we couldn't easily see. Ice structured, like a fragile foam. Fractals that vent without a classic tail, or a flattened, unusual shape. A geometry that changes how sunlight pushes. Explanations stretched, but still tried to stay within nature's boundaries. For 3 Atlas, that same careful framing felt harder, because the glow, it was not subtle. It wasn't a tiny offset, or a small curve that could be nudged. It was a surge, an enormous coherent brightness, and a spectrum that looked too clean, too organized, too persistent. So the comparison revealed a painful truth. science is strongest when it can repeat, when it can watch the same kind of thing again, under slightly different conditions, and learn the rule from the pattern. But the cosmos wasn't offering repetition. It offered a handful, no, in-between objects, no control cases, no second pass, no chance to send a probe and settle the questions up close, just two rare visitors, each carrying a different kind of discomfort, and that absence became its own data point. In public imagination, the past contrast did what contrasts always do. It invited stories. What if interstellar space is not only full of natural rubble? What if some fragments are deliberate, not a rock, but a remnant, not a wanderer, but a relic, a piece of engineering, lost or sent, drifting between stars? Scientists avoided saying that out loud because extraordinary claims demand extraordinary evidence, and evidence was thin, but the idea still lingered, not as a conclusion, as a shadow behind the careful language present in the way conversations paused, in the way conference notes used neutral words to describe something that didn't feel neutral. And tonight, you don't have to decide what it means. You can let it remain, a quiet, unanswered contrast. Two visitors, two contradictions, and a universe that doesn't rush to give us a second example, only the soft reminder that sometimes the most powerful questions are the ones the sky refuses to repeat. The balance was almost too neat to dismiss. One traveler showing motion with no obvious push, another pouring out light, yet drifting as if nothing touched it. Put them side by side, and they read like a single riddle: movement without a clear force, energy without a clear cost. But the deeper contrast, it wasn't only mathematical, it was felt. Oumuamua left the community with wonder, a quiet curiosity that lingered. 3 Atlas left something heavier, a question that wouldn't sit still. One hinted, the other insisted. Together, they stood like markers at the edge of our map, 2 bookends framing years of watching, and in tucked-away notes, some researchers began to describe them differently, not simply as odd, but as boundary points, as if they outlined where familiar physics ends and where new rules might begin. If a 4th or 5th interstellar visitor ever arrives, these 2 comparisons will shape the first interpretation. Until then, the contrast remains, one dim and departing, one bright and unyielding, 2 clues written in opposite dialects of light, and between them a long, quiet, a silence that somehow feels louder than any signal we've captured so far. And in space science, big turns almost always begin the same way, with disbelief. When the early frames of 3 Atlas showed that sudden leap in brightness, the teams at Stereo A, Soho, and GOES 19 didn't rush to call it a miracle. They assumed the ordinary answer. First, that something, somewhere, in the system, it was wrong, because in astronomy, a dozen things can imitate the extraordinary. Glints, cosmic ray hits, processing artifacts, sensor quirks, thermal drift. The first responsibility is to doubt the hardware before you doubt the universe. So began what some engineers later nicknamed the calibration crisis, a concentrated stretch of days spent trying to prove the event wasn't real. The leading suspect was saturation. When a source grows too bright, detectors can overload, and a false curve can appear. Telemetry was pulled, exposure histories checked, gain and offset settings reviewed, dark current corrections verified, and the readouts stayed calm. No overload, no clipped pixels, no runaway auto exposure. Each instrument had adjusted, exactly as designed. It wasn't the sensor pretending, it was the sky doing what it did. Next came the fear of stray sunlight. Maybe a feature on the sun's edge had scattered through the optics and painted a phantom into the frame. Coronagraphs can be sensitive that way, but solar logs told a different story. No matching flare, no coincident burst. The nearest flare had occurred hours earlier, and on the far side, and then there was the geometry. Stereo A, Soho, GOES 19, each looking from a different place. Yet the anomaly appeared in the same relative position in all 3. Stray light doesn't coordinate itself across millions of kilometers, so the team turned to thermal effects, internal. Temperatures can warp readings, especially near the sun, but the thermal sensors stayed steady. No sudden heat spike, No quick cooling, no mechanical drift, and with each ordinary explanation that failed, the uncomfortable option grew clearer. The machines were fine, and the object was the strange part. Still, they kept going, because that's what good analysis does. Calibration archives were opened, old baselines, reference stars, historical lamp, checks, records, stretching back. Years, again and again, the instruments came back with intolerance. That's when the conversation began to pivot. Maybe it wasn't a sensor problem, but an interpretation problem. Maybe we were measuring correctly, but misunderstanding what the light meant. One idea was polarization. If the emission was strongly polarized, it could skew brightness estimates. But polarization implies a preferred direction, a kind of organized structure in the emitting field, hard to reconcile with a small, irregular body. Still, they tested it and found the opposite. The light was nearly isotropic, even unbiased, as though the glow belonged everywhere at once. Then the overlays were excess, made, stereo A against Soho, Soho against GOES, 19, and the fit was unnervingly tight, timing aligned to the minute. Profiles matched within a few percent, different clocks, different optics, different pipelines, telling the same story, and, quietly, a line appeared in internal notes. If it isn't the instruments, then the strain is on physics. Even then, not everyone was ready to accept it. Some argued for software, a shared processing flaw, a pipeline artifact. So they went back to raw telemetry and rebuilt the images from scratch, separate labs, separate code, separate assumptions. The result stayed the same. The signal survived every attempt to wash it away. By the end of the review, the conclusion settled in. Calibration was solid. Hardware behaved. The measurements held. What remained was the story the numbers told. An interstellar body, enduring intense solar conditions, lighting up beyond expectations, and yet keeping its path almost perfectly, unchanged. The failure wasn't in the instruments, it was in the comfort of the old models. Theory didn't shatter in a dramatic explosion, it just showed hairline cracks, the kind that only appear when the universe presses hard enough. 3. Atlas had turned our sensors, tools built to watch the sun, into witnesses of something they weren't built to explain. And when the verified files were finally archived, one report captured the mood softly. We designed these eyes to study the star, and they ended up measuring the edge of our certainty. When the flare at last eased, and the data stream quieted, a deeper question rose. What was this object made of, really? Most comets follow a familiar recipe: water ice, carbon compounds, dust, and stone. Sunlight warms, gases escape, a coma forms, and the behavior feels known. But 3 Atlas didn't follow the familiar script. It glowed like heated metal, resisted the usual vaporization, and carried that blue cast that ordinary ice and dust don't easily create. Whatever it was, it didn't behave like a fragile snowball, so the teams returned to the best tool they had, spectroscopy, the same method that had already hinted. Something was off. In the reflected spectrum, the visible response looked unusually flat until faint absorption notches appeared, subtle signatures where metals can drink in light, magnesium, nickel. In ordinary comets, those traces are weak, diluted beneath the louder story of volatiles. But here, even the quiet lines felt like clues, like the first gentle outline of a material we don't yet have a name for. When sunlight reaches ordinary comet material, it heats, it loosens, it turns solid into vapor. Gas streams outward, and a familiar coma blooms soft and temporary. But 3 Atlas would not follow that old pattern. It shone like heated metal, it resisted the usual boiling away, and it carried a blue tone that simple ice and dust struggled to create whatever its ingredients were. It did not behave like a delicate snowball at all. The earliest chemical hints came from spectroscopy, the same quiet tool that had already revealed earlier oddities. Across the visible range, the reflected response looked almost flat until faint. Absorption dips appeared small places where certain materials drink in, light magnesium nickel. In normal comets, those marks are often subtle, softened by the louder presence of volatile ice. Here, the lines stood out with unusual clarity, sharp, clean, insistent. It made some analysts wonder if the surface was not ice-coated but closer to metallic skin, and still near, perihelion temperatures should have been high enough to soften or melt exposed metal. Yet, the object endured smooth, bright, unbroken. That quiet defiance pushed minds toward refractory matter, the kind that survives where lava is not enough. Materials like tungsten, titanium carbide, and silicon nitride can remain solid beyond 2000 degrees C. They are uncommon in nature, but traces have appeared inside rare meteorites, relics tied to violent stellar events. Such minerals form under extremes, pressure and heat, far beyond the gentle conditions of typical planet building. If 3 Atlas carried a high fraction of that kind of substance, it might have been forged in the debris of a dying star, a driftwood fragment of cosmic metallurgy, wandering between systems for ages. But even that idea met a boundary. The glow looked even too smooth to be the messy blend of random grains. Its reflectivity, its albedo, was unusually high, closer to polished metal than rough rock. It behaved less like stone and more like a mirror held steady in light. Another proposal moved in, from the world of carbon, not soft soot, but structured allotropes. Graphitic layers, arrangements that can absorb harsh ultraviolet and return it as visible radiance. On Earth, engineered cousins exist, graphene-based composites, diamond-like, coatings films designed to manage energy across a surface. These materials can tolerate sharp temperature swings, and they can glow efficiently in ways that resemble the brightness 3 Atlas displayed, and yet such films do not appear easily. They 24 often require slow formation, low pressure deposition, and time the opposite of chaotic stellar violence. So if a layer like that existed out there, it suggested either an extremely long natural polishing history or something more directed, something shaped toward purpose. Few wanted to speak that last possibility aloud, but the resemblance was hard to fully ignore. In laboratories, teams tried anyway, carbon metal composites heated in vacuum, tested for optical behavior. The results came close but never matched cleanly. Artificial samples tended to lose their glow as surfaces degraded, while 3 Atlas kept shining for days after perihelion. That persistence opened the door to stranger materials, exotic glassy shells laced with metallic nanoparticles, a reflective skin that could radiate energy without crumbling, almost as if it could renew itself. Others pointed to alloys born in supernova ejector structures, not found in everyday chemistry on Earth. And another clue kept returning the lack of dust. Normal comets shed constantly when heated, their comas turn messy, their tails grow textured, but the coma around 3 Atlas looked optically clean. It glowed, but it did not shed. That stability suggested a sealed surface, dense, inert, unwilling to sublimate. Observers began using a quiet description, an object that glows without bleeding. By November, some internal discussions at ESA leaned on a careful phrase, refractory interstellar remnant, vague enough to stay cautious, specific enough to admit how strange it was. The words implied something closer to industrial ceramic than cosmic ice, and still the mystery deepened. Light behavior, heat endurance, no noticeable acceleration, all pointing toward extreme stability, whether born by chance or shaped by something more orderly. It began to feel as if 3 Atlas had been sculpted to survive what no ordinary comet should survive. So a question about material quietly became a question about origin. What kind of environment could produce a body so resistant to the sun itself? A supernova heart, a dying star's debris field, or a place where matter is disciplined rather than chaotic? Until another visitor like it arrives, no one can say with confidence. For now, the best approach is simple: listen to what the data demands. In a universe full of fragile dust and vapor, one traveler arrived, made of something harder than heat, something that turned the sun's fury into little more than light. By early November, after conventional explanations had been tested and set aside, a quiet unease began to ripple through the community. The story had survived every attempt to unmake it: vast emission, no obvious mass loss, a trajectory that stayed clean under pressure and endurance beyond familiar natural recipes. At some point, the focus shifted from what it was to why it behaved this way. That shift gave birth to the most delicate idea, the engineered hypothesis. It did not begin in press releases, but in side conversations, in archived messages, in cautious notes. One researcher framed it gently: if an object behaves as if it were designed, the least we can do is test that possibility, not as a claim but as intellectual honesty. In its careful form, the idea did not require intelligence steering the object. It suggested something subtler, that 3 Atlas might be a fragment of constructed material debris from a system that once shaped energy with control. In that framework, the strange properties, the uniform spectrum, the heat resistance, the emission efficiency would not be magic, only leftover traits of something built for endurance. The argument leaned heavily on surface behavior. Near perihelion, it should have boiled away quickly. Instead, it transformed solar radiation into coherent blue light with an efficiency resembling engineered photonic surfaces. On Earth, the closest parallels live in nanostructured films used in optical devices, surfaces built to guide light at very small scales. To find that kind of precision in a natural interstellar body stretches probability even without invoking dramatic stories. Another point returned again and again: symmetry. Luminous envelope around 3 Atlas appeared nearly spherical, expanding evenly in all directions. The case for an engineered origin leaned most strongly on the surface itself. At perihelion, 3 Atlas should have boiled away in moments. Instead, it seemed to take sunlight and return it as focused blue radiance, with an efficiency that felt uncomfortably close to what we see in crafted photonic materials. On Earth, the nearest match would be nanostructured films built for optical devices. Surfaces meant to steer light at quantum scales, to shape photons with precision. To discover anything similar on a natural body crossing interstellar space pressed hard against probability. Then another clue arrived: quiet but striking symmetry. The glowing envelope around 3 Atlas looked almost spherical, spreading outward evenly in every direction. Comet comas rarely behave that way. They are lopsided, driven by cracks, jets, uneven vents. So a balanced sphere suggested regulation, a geometry that responded uniformly to incoming energy. To some researchers, that pointed toward a continuous structure, not scattered rock and ice, perhaps a coherent lattice, crystalline or metallic, able to distribute energy across the surface without hotspots or weak points. Skeptics answered calmly. Nature can create symmetry too: snowflakes, bubbles, magnetic arcs. But defenders replied, those examples usually form in quiet equilibrium, not in the turbulent furnace of a solar pass. 3 Atlas did not merely sit in balance, it held balance while being attacked, a steadiness that refused to fracture. Speculation deepened when the third spectral oddity returned to the table: nickel without iron. In most stellar histories, those metals are forged together. To separate them cleanly often requires selective processes: sorting, refining, filtering. So the data hinted at purification, as if the material had been processed, not simply assembled. There are rare, natural pathways that can create unusual purity events. So extreme they reshape matter, but stacking every anomaly into one object made simple chance feel strained. Some scientists looked backward for context. In 2017, a similar argument flared around Oumuamua. A few voices suggested its shape and motion resembled a fragment of a light sail, a human concept for interstellar travel. That notion was widely treated as speculative, yet later people noticed the echo. Oumuamua showed motion that did not match what was visible. 3 Atlas showed radiance that did not translate into motion. Each challenged inertia in a different way, as if hinting at principles of deliberate efficiency: energy with minimal waste, behavior with minimal loss. No official body endorsed the idea, but it continued to hover at the edge of discussion. Papers stayed careful with wording. They spoke of photonic conversion, material coherence, engineered analogues. The public heard it differently: as a soft rumor that somewhere in the galaxy someone had learned to shape matter in ways we can barely imagine. A whisper, not a conclusion. Even among supporters, the thought carried restraint. It was not a claim of visitors arriving on purpose, more a recognition that intelligence, if it ever existed elsewhere, might leave traces in physical behavior. If 3 Atlas were an artifact, it would not need to be active or aware. It could be like a shard of glass, a durable remnant from a Velifar, technology older than our sun, drifting until gravity pulled it into view. In the end, no one could settle it. The encounter was short, the evidence limited the object, already departing. Still, the idea stayed present, because it shifted the border in our minds. It reminded researchers that natural and artificial might not be absolute opposites. Maybe both are forms of order arranged under the same universal laws. As 3 Atlas moved outward, dimming beyond the orbit of Mars, one truth remained: steady. We had watched a body behave as though it were built to endure the sun, whether shaped by nature or by intentions long forgotten. Its purpose, if it had one, remained unknown. Yet its endurance offered a quiet possibility that Engineering in some distant epoch could be as old as starlight itself. Extraordinary claims ask for extraordinary proof. So when private channels began murmuring about design and plasma coherence, the wider community responded the way science does, with careful doubt, with method, with patience. Skepticism became the engine of the weeks that followed perihelion. For every proposal involving intention or intelligence, a counter-proposal appeared, built to bring the discussion back to physics. The first was statistical and practical. Space is vast, and the range of environments is beyond easy imagination. Given enough time and enough bodies, rare combinations will occur, so uniqueness alone is not evidence of design. Some argued the engineered feeling was simply a mirror of human pattern-seeking. We see purpose because our minds are trained to look for it. A second counter-argument focused on computation. Even when instruments are healthy, data is never pure experience. It is processed through algorithms and assumptions. If three spacecraft saw the same trend, perhaps they shared a subtle bias in the translation from light to numbers, a consistent illusion born from consistent methods. One researcher wrote that we recognize coherence because we build systems to detect coherence. Then a third concern rose: rarity itself. If three atlas truly belonged to an exotic class, where were the others? Why only one? The cosmos rarely offers single examples without any cousins. Some insisted that one of one often signals a flaw in reading, not a new era of physics. They argued that the lack of repetition should weigh against the most dramatic interpretations. Then came a chemistry-based rebuttal: nickel, without iron or emission, without mass loss, might come from layered structure. Some bodies carry thin films that interact with radiation in narrow bands. A crust rich in unusual compounds could filter and glow without invoking intelligence. In that view, precision is not proof of design. Nature can be precise when conditions allow. A particularly elegant reply came from plasma specialists. They noted that plasmas can self-organize. A fast object moving through charged space can set up resonances, standing waves, and symmetric patterns. Order can emerge from instability without any planner behind it. Spiral, galaxies, bubbles, storms all show that symmetry can be a natural outcome of energy seeking a lower state. Even the thermal resilience of 3 Atlas was given a conservative pathway. A naturally sintered crust, a glassy shell formed over many star passages. Over millions of years, repeated heating could bake an outer layer into insulation. By the time it reached our sun, the surface might have been unusually heat-proof. That they would look artificial, but could be cosmic geology, working slowly and relentlessly. A final counter-argument leaned on philosophy, warning against anthropocentric inference. Humans have habit of projecting intention onto what we do not understand. To see design, critics said, might be the same impulse that once placed meaning in every light in the sky. The object did not owe us purpose, and still even rigorous skepticism had a double-take limit. Each rebuttal explained a piece, but not the full puzzle. Brightness, composition, stability, they could be addressed separately, yet the combined package remained hard to unify into one clean, natural model. Supporters of the engineered frame stayed cautious too. They argued that doubt should follow evidence, not comfort. Not understanding is honest, they said, but denying what the data shows is not. By late November, the debate reached a kind of balance motion without closure, confidence without a final answer, a conversation still moving, still circling around a mystery that would not settle. When 3 Atlas swung past the sun and began the outbound path, many expected one simple outcome. The light should weaken the way all comets do. Cooling after perihelion is usually predictable. Closer means hotter, farther means colder. The decline is steady enough that it becomes a tool for checking composition. But again, 3 Atlas did not follow the familiar rhythm. Its cooling curve did not slope smoothly. It seemed to flatten. At first, some thought the record was incomplete. Yet day after day, the brightness held, even as the object raced outward at tens of kilometers per second. That steadiness pressed against the inverse square. Expectation intensity should drop quickly as distance grows. By the third day, most models predicted a major dimming. Instead, the luminosity dipped only slightly, far less than expected. Multiple platforms recorded the same stubborn trend. It was not cooling like a normal comet. It was holding. In ordinary comets, cooling is tied to mass loss. Ices evaporate, absorbing heat, and the nucleus fades as volatiles are spent. But spectroscopy showed no new gas surge after perihelion. No fresh lines, no clear flare of typical byproducts. The spectral bands stayed stable. The surface looked sealed, quiet, inert. If it was not shedding heat through evaporation, then something else had to explain the slow change. One idea was radiative trapping. If a dense plasma envelope surrounded the object, photons could scatter and reabsorb repeatedly before escaping, creating an energy bottle where light leaked out gradually. That matched the smooth behavior, a slow release, rather than a fast fade. But models said it would require a field uniform, magnetically stable and persistent long after. Solar wind should have carried it away. No known comet had shown containment like that. Another approach leaned on thermal inertia. Maybe the body was made of material dense, conductive, crystalline, able to store heat and release it slowly. Yet even high inertia materials should still dim more quickly as radiation escapes into space. Infrared channels hinted the temperature fell only a little, a rate so gentle it felt nearly impossible for an object of that scale. The persistence of visible light opened another doorway: active re-emission. If the surface could absorb ultraviolet and re-radiate it as blue visible light, then optical brightness could stay high, even while thermal energy declined. That would separate cooling from fading, two things nature usually keeps linked. But it also suggested surface chemistry more sophisticated than typical interstellar dust. By the fourth day after perihelion, the object was already millions of kilometers farther out. Still, the brightness curve looked nearly horizontal. On graphs, it became the plateau, a line that refused to tilt downward. Some compared it to a controlled reflector like a powered satellite, maintaining a chosen signature. Others avoided that analogy and called it simply the most thermally stable interstellar object yet recorded. One memo described it in a calm sentence as if it knew how to cool without surrendering its light. Poetic, but it fit the data. Weeks later, the plateau finally began to fall, but not gently. It collapsed. Around day 12, brightness dropped sharply, almost like a switch had been flipped. Some suggested the plasma shell dispersed, or the emission mechanism exhausted its charge. Others wondered if rotation shifted the bright face away from view. When plotted in full, the curve looked less like cooling and more like shutdown, not the fading of a body, but the ending of a process. That distinction mattered. Natural objects cool by law processes can end abruptly. To this day, that plateau and drop remains one of the most unsettling traces in the 3 Atlas. Record a line that stayed flat against expectation, then fell all at once as though it chose its moment to dim. When high-resolution coronagraph frames were examined, researchers expected another familiar shape, a tail pointing away from the sun, driven by radiation, pressure, and wind. Instead, the images revealed a faint linear extension aimed inward toward the sun. It was small, but clear, a blade of light pointing the wrong way. It quickly gained a nickname, the anti-tail. Anti-tails have been reported before, usually as perspective effects. When dust released earlier aligns with the viewing plane, it can appear to point sunward, even while trailing behind in space. But the geometry here did not support that simple explanation. 3 different vantage points still saw the same structure. It was not a viewpoint trick, it was physical, and oriented against the expected flow. The first question was mechanical. How could anything persist toward the source when sunlight pressure should drive it outward? Even dense dust usually yields, yet the anti-tail held for hours, nearly 6, with only a faint ripple along its edge. Its light looked slightly bluer than the main halo, suggesting higher energy emission. That color difference became a clue. One theory proposed a magnetic mirror effect. Plasma around the object interacting with solar field lines could reflect charged particles backward along converging channels, forming a filament that pointed sunward like a solar streamer, but reversed electric fields guiding electrons inward instead of outward. That explained shape and brightness. The line would be plasma, not dust. Another model suggested gravitational focusing. Neutral particles emitted first, then ionized. Later might travel inward briefly before radiation pressure turned them back. But the timing did not fit well. The structure lasted too long to be a short transition, so whatever sustained, it likely had to be continuous, not momentary. Some suggested something stranger still, that the anti-tail was not particles at all, but redirected light, sunlight, entering a refractive shell and being guided along an axis. If the surface were layered or crystalline, it might behave like a lens, but scaling that effect to a kilometer body felt difficult to accept. The steadiness was the most haunting part. Normal comet tails shift constantly under solar wind changes. This line did not waver much. It held alignment as if supported by invisible structure. That rigidity suggested electromagnetic stability, a kind of closed circuit with the solar environment. Plasma physicists noted a basic principle. A conductor moving through a magnetic field can generate current. If 3 Atlas was, to metallic, it could induce current strong enough to organize nearby plasma, creating a luminous filament back toward the source field. Then another feature appeared just before the antitail vanished. Its base brightened sharply, a pulse that traveled along the line, then disappeared. It lasted under 2 minutes, but was caught by multiple instruments. It looked like a discharge. No debris followed. No fragment broke away. The structure simply ended. Space darkened again. When angles were measured, the alignment was striking nearly collinear, with the line to the sun's center off by less than 1 degree. Random outflow rarely holds such precision. In following weeks, papers used careful terms: field-aligned plasma behavior, localized photonic channeling. But behind the cautious language was shared awe, an interstellar body briefly pointing back at the sun against expectation. To this day, that antitail remains one of the most haunting images, a narrow line of blue-white to light against the current of normal physics, as if the traveler turned for a moment to face its star. By late November, as 3 Atlas moved beyond Mars, and its glare faded toward the limits of the major solar observatories, the conversation shifted again from what had happened to what might still be happening. The visitor was dimming, but it was not gone. If it continued to behave outside standard thermodynamics, then the next observation window could become one of the most important campaigns in recent astronomy. The earliest forward projections came from JPL orbital dynamics teams. Using perihelion tracking, they confirmed a hyperbolic escape path tilted roughly 38 degrees from the ecliptic plane. Early February 2026, the object would pass about 1 astronomical unit above the orbital track of Earth, continuing outward into the region between Mars and the asteroid belt. At that distance, sunlight would be thin, and the object would slip below. Magnitude 21, nearly invisible to ordinary optical telescopes, but other senses could still follow it: infrared and radar. The real obstacle was not sensitivity alone, it was choreography. Multiple facilities signaled interest at once. The James Webb Space Telescope, though devoted mainly to deep cosmology, keeps a small allowance for time-sensitive targets. Its near-infrared spectrograph could search for a lingering thermal trace long after visible light fell away. At the same time, Goldstone prepared for radar attempts, hoping for a return strong enough to estimate size, shape, and rotation. And in Europe, the Gaia extension teams discussed a different role, not imaging the body as a picture, but tightening its position through parallax, using precision astrometry across wide field sensors. Together, those tools could build a composite record: temperature behavior, spin hints, and motion over the months ahead. The purpose was simple: test persistence. If the perihelion glow was only a short plasma excitement, then the stored energy should be gone by now. The infrared curve should slope downward, quietly, smoothly into noise. But if the signature stabilized again, if heat or brightness refused to fall, it would imply something deeper, a sustained process in an omniable, unbound interstellar body. That would be a category shift, not just a detail. Engineers at Goddard began drafting predictive tracks, not one forecast, but several competing ones. One assumed radiative cooling from a high reflectivity metallic shell. Another assumed a fading magnetized envelope, a slow plasma decay over a week. A third explored delayed emission, a stored energy leak where luminescence persists after the solar encounter. Each produced a different curve, a different fingerprint. In time, the next window would decide which story matched the sky. The plan sounded straightforward until logistics arrived. JWST cannot turn quickly, and every new pointing request is careful because of its thermal stability. Goldstone time was tight too, already committed to asteroid defense priorities. Still, both sides agreed to carve out narrow openings, minutes of radar, and a brief run of infrared monitoring, enough to catch even the faintest echo. On the ground, large telescopes, also mobilized VLT in Chile and Pan-STARRS in Hawaii, prepared search programs, not expecting a bright target, only a faint reflection, a whisper against background stars. If 3 Atlas retained its unusual reflectivity, it might still appear as a thin, moving trace in long exposures. Citizen science networks were invited as well, a distributed mesh of cameras submitting stacked frames to help refine the fading path. What teams hoped for was not another surprise, but a trend to return to predictability. If the measurements followed a normal thermal decline, the episode could be placed into a category, even if the category still felt strange. But the tension under the planning was obvious. If it deviated again, If it pulsed or brightened or shifted course even slightly, the mystery would not be closing, it would be extending. Inside observatories, the tone stayed professional, but charged pipelines were prepared to capture every photon and automated checks were written to flag any flux above expected margins. Because with an object like this, a small flare is not small. Even a minor uptick could force a new round of theory. By mid-January, the outbound observation window was expected to open roughly 40 days before the visitor would fade beyond detection. In cosmic terms, a heartbeat, one last chance to look before darkness takes it for good. No one could promise what the data would show. Maybe it would finally dim into silence, an odd relic, but still a relic of nature. Or maybe, against probability, it would do what it had done all along, remain too bright, too stable, too orderly for comfort. Either way, the window would not only test instruments, it would test our understanding of what can survive the sun, and what out in the cold quiet refuses to die on schedule. If 3 Atlas fades completely, it will close one of the most baffling chapters of recent astronomy. In months it rejected the usual rules, glowing too strongly, cooling too slowly, enduring too much. And if the final photon is gone, what remains will not be light, but meaning the question of what it was while it was here. For scientists, its disappearance would feel double-edged relief, because a silent object can be archived, measured, contained, and lost. Because an anomaly that vanishes without explanation feels like a dialogue cut off mid-sentence. The universe spoke in a dialect we do not yet translate, and then the channel went quiet. If it fades, naturally, models will eventually absorb the strangeness. The plateau may be reframed as delayed, release the blue tone as an extreme plasma state, the perfect trajectory as symmetric. Emission literature will file it under careful headings, and the shock will soften into footnotes. That is how science digests puzzles, by classifying them until they feel less sharp. But some parts will keep their edge, a spectral line that should not be there, symmetry that resists chaos, and the stubborn quiet of acceleration. Researchers who lived with those graphs will remember the weight, not of drama, but of logic, bending under observation. For them, fading will not feel like an answer, it will feel like distance. Philosophers sometimes say the cosmos preserves its dignity through departure. It never grants endless staring. Galileo watched stars disappear at dawn. Voyager will one day fade beyond contact. If 3 Atlas dims completely, it joins that lineage of unreachable. Wonders proof that the universe keeps secrets, not through malice but through scale. For others, fading will carry a softer interpretation. Maybe the brightness was never defiance, maybe it was farewell, a traveler releasing the last of its stored energy before returning to the interstellar cold. In that sense, fading is not an ending but a return. Stars flare and collapse, comets bloom and vanish, signals peak and dissolve, the pattern repeats, and each time it leaves behind the same thing: hunger. There will be no ceremony when detection ends, only final logs, coordinates, timestamps, and a quiet closure line written without emotion. Yet the silence after will feel like the end of a conversation you did not realize mattered until it stopped. If it fades, it will mean 3 Atlas was mortal after all, governed by physics, not outside it. But it will also mean for one brief interval humanity encountered something that stretched certainty to its limit. It arrived uninvited, lit the inner solar system with impossible precision, and then left, taking its reason with it. And if beyond Mars that last shimmer truly dies, its legacy will not be light, it will be perspective, a reminder that surprise is still possible, and that every glow, no matter how strange, contains the promise of an even greater silence waiting to be understood. And if it holds, if the light does not fade, if the trace remains steady, despite distance and cold, then the boundaries of astrophysics begin to tremble. For centuries we have trusted decay. Heat spreads, energy disperses, light dies. From a candle to a star, that rhythm is a foundation. So if 3 Atlas refuses that rhythm, then something is being rewritten. The first confirmation would be quiet, almost accidental, a late shift at Goldstone, or a JWST analysis queue, someone noticing that the infrared signal did not sink into noise, but steadied, or an ESO log review, showing the magnitude line not falling, maybe even rising slightly. Within hours, pipelines would blaze with alerts, instruments would pivot, schedules would be torn open, the speck that should have vanished would become the most watched point of matter in the solar system. At first, explanations would search for safety reflection off a faint dust sheet, a new viewing angle, a hidden background source. But if the stability persisted, caution would turn into unease because brightness means energy, and energy demands a source. Yet, the source would not be obvious. A steady glow this far out would imply internal stability, an energy process not dependent on sunlight. That is not a minor adjustment, it is a reshaping of thermodynamic expectation. Objects should cool and fade, not hold a luminous baseline. So if it holds either, it is generating energy, or it is coupling to something we do not account for, perhaps the interstellar medium itself. Either way, it would stop being a passive object in our models. It would become a system. The questions would multiply. Could trapped plasma still be oscillating left over from the solar encounter? Could electromagnetic resonance be maintaining a balance like a sustained ring of charge? Or the question that would remain mostly unspoken, even as it shaped the room. Could it be built to hold not a stone, but a structure, not a remnant, but a device like equilibrium? Engineers would compare the signature to familiar human ideas: persistent emission, photonic storage, high Q resonators, superconductive, like behavior, not to claim a match, but because the geometry would feel uncomfortably controlled. If the glow proved sustained, the boundary between artifact and asteroid would blur, and the engineered hypothesis would return not as a rumor, but as a line item to be tested. Public reaction would be immediate. Headlines would call it the light that refuses to die. Feeds would swarm with theories, beacons, probes, omens, symbols. Some would read it as meaning. Scientists would try to keep to measurement not because they lack wonder, but because wonder is not evidence. Time would become the pressure. A week of persistence is an anomaly. A month is a mystery. A year is a paradigm shift. Instruments would be recalibrated again, theories reopened, language rewritten, not to explain it fully but to make room for it, and somewhere in the quiet of a lab, someone would whisper a thought. Too careful for a paper, maybe this is not an object but a continuing process, a still-running equation. If it holds, it forces a change in how we define end states. Because to hold light when it should go out is to resist entropy the most reliable rule we know. Whether through resonance, unknown material, or deliberate architecture, a sustained glow would be proof that endurance can exist in forms we have not learned to name. And if months pass and the light remains confirmed as neither reflection nor artifact, then the universe will have placed a quiet ember in the dark, not loud, not apocalyptic, just steady rewriting what it means to survive the sun. When 3 Atlas first appeared, it was only a new point in a crowded sky. No announcement, no warning, no place in our older catalogues, just another moving dot until it became a teacher. It broke predictions, tested instruments, and showed how tidy assumptions can fail. Whether comet fragment or something, it cannot label it left, more than questions behind. It left a change in perspective, a reminder that the universe can still surprise, and that sometimes the hardest part of discovery is not seeing the light, but deciding what to do after the light refuses to behave. It began as nothing more than a fresh point of light, one more passerby in a sky that is never empty. But what came next changed its role completely. It did not behave like a simple entry in a catalogue. It disrupted forecasts, tested hardware, and loosened that comforting belief that nature always stays neat and always stays readable. Comet fragment, or something we still cannot name. 3 Atlas left behind more than puzzles. It left lessons, quiet ones, the kind that soften the ego. First lesson, seeing is not the same as owning. We like to believe that measurement equals understanding, that a number in a table means we have it contained, but 3 Atlas opened a gap between detection and comprehension. We tracked its brightness, its path, its temperature, and still it slipped through our formulas like fine sand through open fingers. It reminded everyone that observing the universe means stepping into a scale far beyond our instruments. The cosmos does not respond to curiosity on command. It only grants a short listening window, then lets the signal drift away. Second lesson, humility in the face of anomalies. For centuries, each generation has met something that would not explain itself. Comets that ignored expected gravity curves, stars that dimmed with no clear cause, radiation arriving without an obvious source. In the moment, those events felt like threats to reason. Later, they became the doors that opened new rooms. X-rays, radio, waves, dark matter, all of them began as observations that first sounded impossible. 3. Atlas now sits with that lineage. Its contradictions are not proof of failure, they are invitations to widen what we mean by understanding. Third lesson, silence the silence that follows any discovery too large. Translate quickly. When the first data arrived, the noise was immediate. plasma fields engineered, matter living artifact. But as weeks turned into months, and the light either faded, held a change came over the conversation. People stopped declaring. They started listening, not for a final answer, but for repeating patterns inside the quiet. The universe does not need our permission to be strange, and in the end, silence can be the most honest respect we offer the unknown there is. Also a lesson of continuity. This story does not stand alone. It links to Oumuamua, to 2I, Borisov, and to every unnamed speck that has crossed our sky without a label. Each visitor expands the conversation about what exists beyond our neighborhood. Some follow the familiar script, others redraw the map. Together they feel like a syllabus chapters in a course we did not know we enrolled in, where each anomaly becomes a lecture on humility, on probability, on the limits of perception, and perhaps the deepest lesson is philosophical. Ignorance is not defeat, it is fuel. Human strength has never been only in what we know, it is in the refusal to stop asking. 3. Atlas forced a scenario, with no precedent, no comforting comparison, no ready label to paste on the file, and in that discomfort, it reignited something ancient wonder. The same feeling that once guided star charts now guides data decoding. Wonder is not childish, it is the engine of civilization. If the object fades, we learn that some mysteries end in silence. If it holds, we learn that endurance can exist where we expected only decay. Either way, the lesson stays steady. The cosmos is larger than comprehension, and our role is not to dominate but to witness. In labs and observatories, people will keep modeling, simulating, questioning, not because they expect to finish the story quickly, but because they cannot look away. Its legacy will not only be what it was, but what it forced us to become, a species reminded that certainty is temporary, curiosity is durable, and sometimes the greatest progress comes not from answers, but from standing before the unknown and daring to call it beautiful. Every mystery eventually reaches a turning point when speculation must yield to observation. For 3 Atlas, that moment is approaching. The object that once glowed beyond expectation is now sliding outward into cold with only a price. Few weeks left before distance takes it beyond our best tools. Researchers call it the countdown to clarity, the final window before silence closes the door. But clarity here may not mean understanding. It may only mean learning what we are not ready to explain. The countdown began when the light curve settled into stillness. It did not fade like a dying comet, and it did not surge like a powered source. It held steady, calm, as if protecting a deep equilibrium. Trajectory projections suggest that by mid-February 2026 it will slip beyond radar, reach and vanish from the field of the major telescopes. Between now and then is a narrow corridor, about 40 days, where science must decide what it can or admit what it cannot. Inside, control rooms, the mood is methodical and quietly charged. Every hour of telescope time matters. JWST will aim its infrared instruments at the coordinates, searching for faint thermal echoes. Goldstone will send a final radar pulse, hoping for a 2 return signal sharp enough to hint at size and spin. The ESA, Gaia extension, will refine the track, checking whether the path remains purely Newtonian or whether some hidden influence still lingers. Each instrument offers only a fragment, one narrow lens through which the universe might speak one last time. For the teams involved, this deadline is not only technical, it is emotional. Years of argument have formed 2 incompatible stories. One story says natural matter at the extreme edge of physics, a relic of chemistry we have not met before. The other story whispers structure, design, purpose. Not proof of intelligence, but a hint that matter itself may remember how to organize beyond our comprehension. This last campaign will either quiet those whispers or amplify them if the brightness holds. It could become the first recorded case of an unbound interstellar body, maintaining behavior that looks independent of solar input. That single result would press on many fields at once: thermodynamics, plasma, physics, materials, science. If instead the glow fades in a smooth, predictable curve, the tension will release like a long-held breath. Scientists will return to familiar language: cooling, dispersion, equilibrium. The episode will be filed as extreme but natural. The world will move on and the mystery will retreat into archives. Yet many quietly suspect 3 Atlas will not cooperate. It has resisted too many expectations already. Its light has felt less like decay and more like persistence, a faint, stubborn heartbeat from a system not finished. So the countdown is not only toward clarity, it is toward confrontation between the universe we think we understand and the universe that keeps surprising us. Outside the labs, The public watches too. Headlines track its dimming like a pulse across the sky. People speak of it as a symbol: endurance, mystery, humility. Inside the observatories, feeling is quieter, almost reverent. Each photon that arrives is a message from something ancient, something that may never pass this way again. When the window closes, clarity may not arrive as revelation. It may arrive as acceptance that knowing has limits, but looking does not. The final images will not seal the story shut. They will only preserve a moment, the last recorded shimmer of a traveler that came from darkness, met the sun, and left behind questions bright enough to outlive its light. And if you felt that quiet wonder with me tonight, the kind that doesn't need answers, only attention, then I'd love to keep traveling together, gently, story by story, sky by sky. So if you want more nights like this, please tap like, subscribe, and leave a comment with the mystery you want next. It helps this channel reach the people who need a softer place to land. And if you're listening to fall asleep, you can do one simple thing. Just let the next breath arrive. Slow, easy, and unhurried. I'll be here again with another calm story waiting in the dark. Until then, good night, sleep well, and let the universe keep its secrets for now.